My honor to welcome our CVR Vista Seminar speaker today, Pascal Mamassian from the CNRS and Ecole Normale, Superior, Paris. So any number of us, I think, could be introducing Pascal today, but I think I'd just put my name forward first, so I get the honor. Pascal is a very well-known vision scientist, and you can see from his title slide the breadth of research that he's made major contributions to, including depth perception, motion perception, multisensory integration, and now, metacognition and many other areas of perception. Just a brief history. I met Pascal way back at Cold Spring Harbor School. And at that time he was completing his PhD at Minnesota with Dan Kirsten, psychology. He went on to Max Planck, NYU, and then the faculty position at the University of Glasgow. And then went first of all to Paris 5, René Descartes in Paris, and now is at the Ecole Normale in Paris. So in addition to making major contributions to research, Pascal's really made huge contributions to the vision science community as an organizer. So for example, we were just talking about ECVP, so he organized a great ECVP in Glasgow many years ago, and then of course became the president of the Vision Sciences Society and organized that meeting. He's received many awards. He gave the Perception Lecture at ECVP in 2016 and received the Annelies Meyer Award from the Humboldt Foundation in 2018. So welcome, Pascal. Great to have you here and looking forward to your talk.
Thanks a lot, James. I'm going to stop sharing that screen and I'm going to put up my slide instead. How is that? Do you see this?
It's good.
Great. So thanks a lot, James, and thanks everybody in York and elsewhere for having me in your seminar series. It's a great pleasure to not be there in York. I would really have loved to be with you, and I know that this context is making these virtual meetings necessary, but there's something more in having face-to-face contact, and I'm sure that we're going to get back to this world enough soon. Today, I wanted to talk about different kind of experiments that we have been running in the lab over the last few years. They all linked to visual perception, and in particular, contextual effects on visual perception, both spatial contextual effects and temporal contextual effects. These contextual effects introduce some biases in what we perceive, in how we perceive, in when we perceive things. And I think these have some implications about what we call nowadays metaperception or visual confidence. Visual confidence or metaperception is the perception of our perception, is how well we trust what we perceive. So I would like to start with a simple forward, very simple, that what we see is not just the light that strikes our retinas here and now, but that our visual experience is dramatically influenced by spatial and temporal contextual effects. And I could have chosen 10,000 different illusions. I'm just showing here one particular one on brightness perception, where the small diamonds that you have on this checkerboard are all the same luminance on the screen. I can show you this by covering one part of the checkerboard. So all these diamonds have the same gray levels in the screen, but some of them are perceived brighter and some others are perceived darker, depending on the spatial context. And yet, we are rarely aware of these perceptual biases, these perceptual illusions. And the questions I would like to come back towards the end of the presentation is, are we authorized to say that then our perception is a form of overconfidence, in the sense that we trust what we perceive, but what we perceive is not correct. So maybe we are overconfident in over-relying on our perception. So let me try to go back to that question towards the end of the presentation. But of course, you all know that there's a huge and very long and diverse literature on biases in perception. I'm going to just to present a couple here. There's the very famous Virort's law in time perception that says that short durations in series are perceived longer than they really are, and long durations in that series are perceived shorter. And that's a kind of a regression to the mean in a sense. And this kind of regression to the mean was made more generic by Hollingworth in his very famous central tendency of judgment that states that an element in a series tends to be perceived like the median of the series. And I can give you, again, several examples. I'm just going to show you some that you all are familiar with. One special contextual effect is the tilt illusion. If I take these two horizontal gratings here that I place inside these larger rings that are tilted clockwise and counterclockwise, you tend to have a repulsion that is the horizontal grating now no longer appears horizontal, but appears tilted counterclockwise relative to a clockwise background. In terms of temporal context, again, I could have chosen different examples. The best ones that work in our lectures are adaptation and After Effects. So I cannot help sharing with you a typical color After Effect example here. If you fixate the black cross in the center here for a few seconds, just look at that cross for 2 or 3 more seconds, and I'm going to replace that image with another image that is just going to be the background image. I'm going to do that in 3, 2, 1 now. Just keep fixating the black cross. And as you are fixating, you might experience some color after images, negative after images. So whenever you were perceiving green, you are now going to perceive maybe some reddish color. Whenever it was yellow, you're going to perceive maybe something bluish. But maybe more interestingly, there might be some small differences. If you keep fixating sufficiently long enough, there might be some small differences between the after images you had on the top and the bottom part of the image. Do you want me to try that again? No.
That would be great, actually, if you do it again. Yeah.
Okay. So, so if you fixate, now that you know what you are supposed to see, you are fixating here. These bottom ones are just there to remind you what are the colors that you are adapted to. And I'm going to replace that image in 5 seconds. 5, 4, 3, 2, 1. Now, keep fixating. And you might experience maybe a stronger after effect on the top part, maybe a long-lasting after effect. These are due, of course, to the contours that are on the top part that are absent in the bottom part, and the contours are there to anchor the color after images. So that's just to remind us that after effects are not just happening in the retina, but they're happening. The whole visual system is adapting. In particular, the visual cortex is adapting, In our visual system, in our visual context, we have orientation sensitive cells that are allowing us to anchor the after image. And since you seem to like this effect, there's this very nice demo from John Sadowski. If you fixate the blue dot for a few seconds, this image is going to be replaced by another image just afterwards, just in 5 seconds or so. Just keep fixating the black dot in the center. Keep fixating the black dot. And if you did that fixate well enough, you might experience a nice colorful castle, when in fact, what you have in front of you is just a black and white image. So it's just relying the same trick of adapting to the negative color images, and the structure of the image here is here to anchor the color after effect, and that makes this effect much stronger than the usual adaptation to just uniform patches. So what I wanted to present today is 5 quick experiments on this kind of spatial, temporal, contextual effects on perception. The first experiment is on when we perceive an event, and when we perceive an event, how is that affected by other events before or after that event? This is some work that a PhD student of mine, Lubica Jovanovic, did a couple of years ago. And again, the aim here is to try to estimate when you perceive something. So when you perceive something is a bit of abstract. So to try to crystallize that question, we presented a time frame to participants. Our participant learned this time frame of 2 seconds. They learned the fact that things would be presented in this temporal frame of 2 seconds, and they were familiarized with these 2 seconds by seeing over and over again a clock that is rotating, a hand of a clock that is rotating at 0.5 hertz. So it's making a full revolution in 2 seconds, and you keep seeing that hand of the clock rotating, and it makes 2 seconds to make that full revolution. Once you're familiarized with these 2 seconds, with this time frame, we then present 2 events within these 2 seconds. Say a red dot, and maybe sometime later a green dot. And after the end of the time frame, we ask you to estimate when one of the 2 events was presented. Either the first one or the second one, either the green one or the red one, but you know that only after you have attended to both of these events. And you make your response about when you think you have perceived that red dot by placing a white dot on the ring of the clock at the location where the hand would have been if it had started to rotate at the beginning of the frame and finished at the end of the frame. Okay, so you see 2 events within the time frame. You are being told which of the 2 you had to make a report, and you report that by placing a white dot on the ring at the location of the hand where it would have been at the time of the presentation of the red dot. So here are some results. I'm going to plot the temporal error that you make when you perceive the target as a function of the time delay between the distractor, the other event that you were not supposed to report, and the target. And when you look at the data, you find this error function. The errors are not 0, they are not uniform. They do depend on the distance between the distractor and the target in such a way that the perceived time of a target that is post-cued by its color is attracted towards a nearby distractor. So it's a kind of attraction towards the other event that you have attended, but that you didn't have to report. So that was a quick one, but the next one is a longer experiment I'm going to talk about. It's linked to how a perception of depth is affected by other objects in the scene. And again, yes, sorry.
So I don't know, maybe you'll get to this by integrating these multiple experiments, but do you have any thoughts about if there's any functional purpose to that bias, or do you have a mechanistic explanation, or is that coming at the end?
I won't have like the full theory, but I don't think that you need to have a functional purpose every single time. But in that previous experiment, when you tend to perceive one event closer to the other event, the fact that you have to attend to both simultaneously shrinks the time around these two events and bring them closer together. So it's related to the next experiment I'm going to talk about, in the sense that when you have to attend to things that that you don't know in particular which one is going to be more important than the other, you tend to group them together, and this tend to make them closer to each other.
So should I think of this as, you know, some people think that spatial attention has a unitary form, and this is sort of the analog of that in time? Is that what you're saying?
I wouldn't go as far as that, especially in front of very smart people in the audience, but I can come back to that. But maybe quickly, another question.
Yeah, I was just following up on that. So if you just present the two events, but you don't need to attend to both of them, does the effect disappear? Like if you know you're looking for the red one? So
the effect doesn't disappear, but you can turn it around by telling in advance which event you have to attend to. That's the kind of experiments that are in this paper that I was talking about. By queuing the target either before or after, or queuing the target by its color or by the order. If you know that you have to attend to the first or the second before the targets are being presented, the effects are very different. And we don't have a full understanding of all the different effects, but I think indeed this is really important. But let me move on, because maybe some of these questions are going to make sense when you see that several of these studies. So as I was saying, the next experiment is on stereopsis. And you all know what stereopsis is, but I couldn't help showing to you the street next to the lab where I work now. Binocular disparities is a very strong cue to extract depth. And you have illustrations of these binocular disparities in these stereoscopic views of Paris, where I have taken two features in the left and right images, the top of the Pantheon building here on the left, and the top of the umbrella of this person here on the right. And the small disparities between the left image and the right image can be translated, could be interpreted as different depths. The umbrella is going to be closer to you than the top of the Pantheon. Binocular disparities is one of the strongest cues to extract depth. It's very, most people are very sensitive, although 5 to 10% of Westerners do not have a binocular vision, stereopsis, sorry. But within that framework of stereopsis, there's a very, very strong phenomenon that is not studied well enough, except in York, of course. This phenomenon, we can call this phenomenon the Westheimer and Mackie phenomenon, because Gerald Westheimer and Susan Mackie have explored it quite extensively in the late 70s and early 80s. This phenomenon is the following. If you present two vertical lines at different depths and ask participants to estimate which of the two lines, the one on the right or the one on the left, is closer to you, people are usually pretty good at that. That's a typical stereo acuity judgment. But when you connect the two lines together so as to form a single object, like a square or rectangular object, and you ask people to estimate, is the right edge or the left edge closer to you, then people start to be very bad at this task. And indeed, Westheimer and Mackie looked at this and other slightly modified versions of these stimuli. And as soon as the two vertical lines were connected, your performance dropped. But in some cases, the objects don't have to be really physically connected. They could be connected so as you to think that they were forming a single object in a single depth, in a single slanted plane. But if they were still decomposed into two separate objects, your performance became good again. More recently, Leslie Dees and Laurie Wilcox in York did investigate that Westheimer-Mackie phenomenon, and again found similar results, where if you had to make a judgment between objects, your performance was good. If you had to make a judgment of depth within an object, your performance was quite poor. So we were also interested in these stimuli. We went back to the Westheimer and Mackie stimulus, and we just duplicated it. And in such a way that by keeping the same frontal view, that is the same lines connected so as to form a rectangle, we could present two different type of stimuli, either stimuli where you are seeing slanted planes that are slanted to the left and slanted to the right, then slanted to the left and slanted to the right, or by connecting the lines that had the same depth, you would be seeing a frontal parallel rectangle at one depth and another one closer and another one further, another one closer. Importantly, in this case, the image that you have monocularly is the same. You have the same vertical lines. The disparity is also the same. The same edges are being used to create either slanted planes or frontal parallel planes. So you have the same information in a sense, but your experience of these two conditions is completely different. If some of you can refuse, here are some images for you to try to refuse these images. The top row is this slanted plane stimulus, where you see a plane slanted to the left, and then next to the slanted to the right, slanted to the left, slanted to the right. And the bottom row is our rectangles that are frontal parallel, one in front, one in back, one in front, one in back. And some of you might experience an easier way to see depths in the bottom row, and a harder way to see depths in the slanted planes in the upper row. So we went to measure that a bit more carefully. We had three conditions. One where we presented just single lines, and we asked people to tell us whether it was the line on the right or the line on the left that was closer to them. All the lines could still be there, but they were connected to two other lines that had the same depth, so as to form frontal parallel rectangles. Or we added two more lines so as to have like 6 vertical lines now, and connected successive lines together so as to form slanted planes. So planes slanted to the left, to the right, to the left. But the task is always the same. People have to keep fixating, and they have to attend to the two lines closer to their fixation and to report which of these two lines is closer to them. And we manipulate the horizontal disparities between these two lines. So here are the 3 different conditions, and here are the 3 results for these 3 different conditions. The horizontal axis here is the disparity between the two lines, and the y-axis is the proportion of time that people reported seeing the right line in front. When the two lines are in isolation, you have the typical stereo acuity sensitivity. When you present two more lines so as to form frontal parallel rectangles. Your sensitivity is more or less the same. It's maybe slightly better because you have a bit more information. But when you connect these two lines so as to form a slanted plane, now your sensitivity to judge whether the right line is in front of the left line drops dramatically. Sorry. And for some people, you could be increasing the disparity of the stimulus without having people reaching ceiling performance. So what is going on here? So let me try to give you an intuition for what might be happening when you group these two lines together. We start with vertical lines. Each vertical line has a particular disparity. This disparity can be represented as having some kind of uncertainty about its depth information. So each vertical line here could be associated with a likelihood of a particular depth by this continuous function here. So that's the uncertainty of the disparity for the line in the back. In dashed, this is the disparity uncertainty for the line in front. For the other configuration where I'm connecting these two lines so as to form a slanted rectangle, again, I'm starting with the same information from the uncertainty of the two lines. Now, these two lines being connected together form an object. The object as a whole has a depth, and we can estimate the depth of this overall object in some kind of Q combination. There are two Qs coming from the two isolated lines. We can combine these two together in some kind of maximum likelihood estimation, but that you can choose whichever framework you prefer to estimate this combined object depth uncertainty. And this is presented here in green. The next step then is the interesting step. Now that you have this overall object uncertainty, the idea is that this overall object uncertainty is spilling over the uncertainty of the elementary features. So each elementary line now is having a new updated uncertainty, which is a linear weighted combination of the original uncertainty that it had before being grouped and the grouped object it belongs to. And for the line in the back, the new line uncertainty is shown here as a continuous line. And for the line in front, the new line uncertainty is the uncertainty in dashed. This is not an optimal rule. Before James is going to ask me that question. This weighted linear combination is nowhere optimal. But this is what is being assumed by this model, that the object uncertainty is contaminating the uncertainty of the isolated line. So that's what is happening for when the two lines are connected to each other. When the two lines are belonging to separate objects, the object uncertainty is still at the same depth, and it's actually helping a little bit the original uncertainty. So there's no detrimental effect of grouping these two lines when they have the same depth, because the object depth has the same value as the original line uncertainty. And you can use this framework to then predict what would be your performance in being able to say whether the line in front is indeed in front or in the back by looking at some kind of discriminability between these two distributions. So it is some kind of receiving operating characteristic curve. Sorry. What is interesting is that this framework is predicting that there will be a ceiling performance for this condition where the two lines are connected together to form a slanted plane. you will never reach seeding performance. And indeed, this framework was used here in the data that I showed. The continuous line was actually the model fit of on this data. And it does show this kind of plateau of performance. In that same experiment, actually, there was a fourth condition on the same participants. In this fourth condition consisted in presenting two slanted planes. They were parallel to each other, but they were slanted. They had the same slant. And they could be positioned at different depths. And the task is again exactly the same. People have to fixate and to attend to the line closer to them on the right side and left side, and report whether it was the line on the right or the line on the left that was closer. But now you have these lines that belong to slanted planes that are parallel to each other. And for this fourth condition, here are the results for the same participants across 5 different values of slant. Again, the abscissa here is the disparity of between the two central lines, and the ordinate is the proportion of time that the right line is perceived in the front. And now what you can see is that there's in addition to the sensitivity difference that we had in the previous experiment, we also have a bias. There's a significant bias that is introduced by the slant. And the continuous line here is actually the prediction from the same model. And I should mention that this is not a fit to that particular experiment. The model was fitted to the first experiment and is just shown here as on top of the actual data. So the conclusion from that study was that your things as very fundamental as stereo acuity could be influenced by whether elementary features belong to an object. And the important aspect of the model in that study is that the object carries some uncertainty and in a dynamic way influence back the features that were used to create that object in the first place. The next study that I wanted to briefly talk about is how object category could be influenced by perceptual history. And again, here there's a very long history of very good studies on how what you perceived in the past could influence what you perceive now. But we're going to present our own work here. What we are interested in here is looking at the perception of an ambiguous pattern that could be seen as biased to the left or to the right after seeing non-ambiguous stimuli. So we're going to try to bias your perception at one particular time based on your history of what you have been perceiving non-ambiguously before. And to do that, the ambiguous stimulus that we are using is a binocular Raveler stimulus, where the left eye is seeing one particular orientation and the other eye is seeing the orthogonal orientation. And your task is going to report not so much the orientation of the stimuli, but the spatial frequency. That is whether the stimulus has a high or low spatial frequency. And I'll tell you why we did that. But behind that, we are interested in whether you perceive left-oriented or right-oriented stimulus. So that's the ambiguous stimulus. It's Raveler's, so it's ambiguous. You could see seeing one or the other. But before seeing that stimulus, you see a whole series of non-ambiguous stimuli. Non-ambiguous in the sense that both eyes see exactly the same thing. So they could be seeing a left-oriented gabor. A bit later, they could see a right-oriented gabor, and you could be seeing a left or right a number of times in a sequence. And after seeing a whole bunch of these left and right-oriented gabors non-ambiguously, then you are presented with Raveler's stimulus, and you are being asked to report whether the stimulus is low or high spatial frequency, just to try to divert your attention away from what the dimension that we're interested in, which is orientation, and the spatial frequency is lower or higher than the spatial frequency of the stimuli that were presented non-ambiguously before. So let me go back to that slide. So we're interested in looking at, say, that particular stimulus, Ravorus, that is ambiguous, and try to estimate whether the fact that you perceive it left-oriented is linked to all the stimuli that you have been perceiving before. So we're going to look at not just the stimulus before, but like a stimuli within a window and within different positions relative to your current position, current time of the stimulus. So we're going to look quite far in the past, in a sense. I'm going to divide the results in two main categories, depending on whether the stimuli that you have experienced were left-oriented or right-oriented a few seconds ago. So within a small temporal window that was in the recent past. And when you look at the statistics of left orientations in the last few seconds, so the more left-oriented you have experienced, the less left orientation you're going to perceive now. So it is some kind of negative after effect with the recent past, just like the color after effect that we have experienced before. The more you see left, the less likely you're going to see left again. So that's the classical negative after effect.
Pascal, can you clarify what you mean by seconds ago? Yeah.
I'll tell you that in a second. Okay. But when you look at the more distant past, now the story is completely different. If you look at the proportion of left over a temporal window that is longer and further back in time, now the proportion of left in that time window is influencing positively what you perceive now. So there's a positive correlation with the remote past. So James was asking, what are these recent and remote past? The time windows that we were chosen here. Of course, we looked at all time windows, and the paper does include all these analyses. But I wanted to summarize the main findings here. There are two main different time windows that you can maybe focus on. A recent past in the last 10 seconds that is responsible for your negative after effect. And these older, more remote past were taken from a time window that is large, over 5 minutes, that was placed up to 10 minutes in the past. So you're collecting quite a lot more information here over a long time window. And this is kind of updating your prior, if you're thinking in terms of Bayesian terms. So you're updating the statistics of your environment in a sense. And these two findings could be summarized in the sense that the new percept, what you perceive now, is making the recent past, the recent statistics, more like the overall statistics of what you're experiencing. With Nikos Gekas, more recently, we went back to these studies and tried to look a bit more extensively. We use the same kind of paradigms where you are looking at an ambiguous stimulus, relatively ambiguous stimulus at one particular time, and on that particular stimulus, you're going to make a judgment about its orientation. And before this ambiguous stimulus, we present less, or let's say less ambiguous stimuli, or stimuli that are at least you're not responding to. So you could be presented with 12 different oriented stimuli to which you're not responding. And at some point, you present one more stimulus just before a reference probe, and you use that probe to make a judgment of whether the orientation of the test stimulus is falling in the green region of the probe or the blue region of the probe. And we keep repeating this. So you do another range of adapting stimulus, you present a test stimulus, and then you make a response, and you keep doing that. The adapter stimuli, the ones that are shown before the test, are drawn from a Gaussian distribution of orientations. So you're not always perceiving the same orientation. The orientation that you see here, of the stimuli that you're not responding to, they are drawn from this Gaussian distribution of orientations. And this distribution is such that it has a mean that varies in time. And the mean is varying in time across the whole block of the experiment. So the mean of this adapting stimuli could be slowly varying clockwise to counterclockwise, and then accelerating in its variation. That's for one group of the participants. And for the other group of participants, the mean could be decelerating in its over the whole block of trials. I think I forgot to mention that the test, which is important, the test stimuli are always presented at the point of subjective equality. That is relative to this orientation here. The test stimulus could be slightly clockwise or slightly counterclockwise relative to the reference, and that particular orientation that is for the test is at the point of subjective equality. So we are really near, yes, at the most ambiguous location. So here are the results for the two different groups on the top and the bottom. The adapting stimuli are shown here in orange. The data are shown in black. The fact that and the stimuli here are average over a small temporal window. So that's why you have this kind of oscillating pattern here. The main thing from the data that we see is that they are opposite to the adapting pattern. So the main thing we observe here from these experiments is some kind of negative outer effect. But there's more to it. And what we are interested in is really capturing the whole all the features of these data. That's why we have been running a model that I'm going to try to explain in a couple of slides. This model is trying to capture the whole history of what you have experienced. So it's going to put some weight on all the stimuli before the current test stimulus. It's going to put either a negative weight if that previous stimulus is going to influence negatively, like with some kind of negative after effect the current stimulus, or a positive weight if it's going to influence it positively. And we can extract the overall history function by doing some kind of reverse engineering here. And this is the kind of weight matrix that you obtain to try to predict the best you can your data. This history function has three main components. There's a strong initial negative component just for the stimulus just before. The next few stimuli in the past are also negatively correlated with your current percept. And then if you go further in the past, again, there's now a positive effect of what you have experienced a long time in the past is positively correlated with what you're currently perceiving. So these positive weights are very small, but they extend over a very long time window. So that overall, if you look at the cumulative effect of all this past history, this cumulative effect is accounting for about half of what you perceive now. And the negative effect is the other half. Okay, so again, nothing really special here except that history effects are well known in perception. There's a lot of work on serial dependencies these days, But I think it's nice to keep in mind that there are multiple timescales playing simultaneously, and your visual system is adapting, maybe updating its prior knowledge across a long time window. And there's another time constant for more local things happening in time. The next topic I wanted to briefly talk about today is on internal perceptual states, and I'm going to try to explain that with this very simple demonstration from Fred Atnev on ocean transparency. You all know this demonstration of a transparent sphere that is rotating, and because it is transparent, covered with white dots, you might be perceiving us either rotating clockwise or counterclockwise if you look at it from above. So we use this kind of ambiguous stimuli. We simplify the stimuli. We don't need to have like a rotating sphere. We can just have two planes translating one on top of each other. And we color the dots as white or black so as to simplify the response from the participants. So you could be asking, you could be judging whether the white dots are in front or the black dots are in front. And then we use this stimulus and we present it at different directions. So the two direction of the dots always move in opposite directions, but the axis of the stimulus could be varying from trial to trial. But your task is always going to say whether the black dots are in front or in the back. So this is some work that we did a long time ago in Glasgow with Julian Wallace. Here are some two participants. The abscissa here is the direction of the black dots, and the ordinate is the proportion of time that the black dots are perceived in front. Again, two participants. The participant on the top here is behaving in such a way that whenever the black dots move downwards and slightly to the left, the participants were seeing these black dots in front. So black, when it's moving down and to the left, is perceived in front. And when the white dots are moving down and to the left, the white dots are perceived in front. So whatever surface is moving down and to the right, that participant is perceiving that surface in front. Another participant here is having the same kind of bias to see everything moving downwards as moving in front, but even with a very much higher sensitivity. You can rotate the stimulus slightly by 15 degrees and completely change this bias to perceive either one surface in front, one surface in the back. Again, two different participants. Each participant, in fact, has his or her own bias to perceive one particular direction in front. These are just two, but we went further to look at more than 30 participants, and we found a bimodal distribution. We found about half of these participants who had a bias to perceive downwards in front, and another half of participants who had a bias to see a rightward motion in front. And more recently with Mark Wechsler, we ran some online experiment collecting data across a much larger population range. And we found again this kind of bimodal distribution. We have quite a lot of participants who prefer to see downward motion in front, and another set of participants who see rightward motion in front. Again, here there's, in terms of utility, there's no right answer. There's no functional utility in seeing one particular direction in front. But your visual system has broken the symmetry in a sense and has biases to perceive one particular direction systematically in front of the other. And this bias is idiosyncratic. One person will have a bias that is different from another person. With Mark Wechsler, also, we were able to collect the data for some participants every single day across 3 months. And these biases, most of the times, are quite stable. That is, across 90 days, collecting data every single day, you're biased to see one direction in front for this participant. This participant saw downward motion in downward slightly to the right in front. But some other participants had a drift of their internal bias across days, a regular linear drift of maybe 3 degrees per day. And some other participants had a bias that was drifting for like a month, had a bad day, and then the bias was then staying stable. So there's a whole range of interesting dynamics to be studied here. Here, I think we're looking at the internal biases of the neural population that is responsible for our perception of motion transparency. And there are some maybe small asymmetries, small imbalance between the neural population that is creating these biases. And the last topic I wanted to cover today is the question I was asking at the beginning. When we look at confidence, what are we talking about? So confidence, again, in visual perception is our own evaluation of the validity of our own perception. But when we are faced with the different biases, what should we really talk about here? Should we talk about the true state of the world or our own internal response? So we looked at this issue of confidence with Baptiste Casio in the context of adaptation. So let me run through this experiment. We are presenting a brief adapter, a color patch that could be either red or green, and a test stimulus that is mostly gray, but could be having a small tint of red or a small tint of green. And the task of participants is going to decide whether this test stimulus is either more red or more green after being adapted briefly to a clearly red or clearly green stimulus. Okay, so that's your perceptual judgment. This judgment is interleaved with another judgment, which is not on color perception, but on orientation perception. And again, here, you're going to make a judgment about a test patch that is relatively ambiguous, but preceded by an adapting stimulus that is presented very briefly, but long enough for you to adapt. So you could be adapting to a left-oriented grating that is going to create a rightwards tilted test perception for the test stimulus. Again, here you're testing, you're reporting whether the test stimulus is tilted to the left or to the right after being adapted to a clearly left or clearly right orientation. Okay, so you're interleaved, you go back and forth between these two tasks, color and orientation. And every two judgments, we ask you which judgment you feel more confident that you responded correctly. Do you think that your color judgment was more accurate than your orientation judgment? And then we repeat that. We do another color judgment, another orientation judgment. And on these last two responses, which one do you think you're more likely to be correct? The orientation or the color? And we keep going. So here are the results. First, for these perceptual judgments, this is for the color judgment, but the orientation is the same. There are three curves here corresponding to the three adapting states, whether you presented a clearly red, clearly green, or a neutral patch before the test stimulus. The abscissa here is the color gamut of the test stimulus, and the y-axis is the proportion of time that you perceive the test stimulus as being green. basically you are able to do the task. That's the black curve. But when you are preceding the stimulus by a red patch, you have a negative after effect in such a way that you are going to respond more green. So this shift to the left or to the right is reflecting a negative after effect. Now, looking at the confidence judgments, we can look at the proportion of time that you were saying that the color judgment was more confident than the orientation judgment. And again, here you have three curves corresponding to the three adapting states of the adapter here. And these curves are shifted by exactly the same amount as the psychometric functions here. So the confidence closely follows the biases. And you can also look at the reaction time to respond red or green or left or right. And these reaction times are slower for the more ambiguous stimuli. And again, you can look at the amount of shift, and the amount of shift is identical here for the response times than it is for the psychometric function. So you're, in a sense, your confidence is closely following the biases. The biases is driving everything. The biases is driving your response times, but it's also driving your confidence judgments. And I want to conclude with this because with a statement about what confidence should actually be. Confidence in the literature is defined as an estimate of the probability of being correct, given what you have just perceived, and given some internal decision variable, some sensory evidence of some sort. And the sensory evidence is linked to the physical strength of the stimulus and some internal sensory noise. And the whole enterprise of studying confidence is estimating the extent to which participants are able to infer their sensory noise. How much knowledge do you have about your own internal noise that is corrupting your ability to perceive correctly the stimulus? The problem is that if you have a bias, and this is an illustration here, this is just simulation data. If you have a bias that is shifting your psychometric function to respond that the stimulus is positive as a function of the stimulus strength, by having some kind of criterion above which you are responding only that the stimulus is indeed positive, your probability correct function is having this shape. It has a discontinuity at the physical truth of when the stimulus is actually zero. You are either responding correctly if the stimulus is slightly positive, and correctly if the stimulus is slightly negative. So maybe this way of thinking about confidence by relying heavily on correctness is maybe misleading. And maybe something more interesting is the notion of self-consistency. Instead of correctness, people could be looking at self-consistency, which is the probability of perceiving the same thing given the same stimulus. So if I keep presenting the stimulus over and over again, am I going to see the same thing, or am I going to have a different percent? And the probability of self-consistency for the same kind of simulated data is now this nice continuous function. So arguably, we should define confidence as the probability of being self-confident rather than correct, given our percept, and given some kind of confidence evidence, which might or might not be the same thing as the sensory evidence. And in parentheses, bringing in confidence evidence is allowing us to talk about other sources of noise, internal noise, that is affecting specifically the confidence without affecting the sensory evidence. So that's all I wanted to talk about today. Again, I presented 5 different experiments, but this is really the work of several very, very smart and good people in the lab. And thank you a lot for your attention. And I'm looking forward to your questions.
Awesome. Thank you, Pascal. It's really interesting set of experiments. Okay, so we have lots of time for questions. I'm not sure which hands went up first, but I saw Rob's first.